for data scientists. And we're going to cover, our approach to operational ML that we call MLOps, and also provide a demo that shows you kind of as a data scientist, how you can take your machine learning applications into production and how you can work with the rest of the team in your company to make these applications successful and continuously improve them in production. I'm joined today by Craig Michaud, who is our sales engineer, who will be running through the demo, as well as Sindhu Ganta, our senior data scientist, who is available to answer any questions. So the first thing we're going to cover is sort of the state of machine learning kind of in production. So there's tremendous excitement about machine learning across the industries, and for good reason, because the techniques have shown such great potential. However, what people are finding, particularly in the enterprise business side, is that they're having difficulty bringing these exciting innovations into production. And so what you're seeing here is a study by McKinsey Global, where basically what they interviewed a large number of enterprise businesses and found that most of them struggled with getting their machine learning projects or their AI projects past the experimental stage. However, the ones that were able to get it past the experimental stage actually saw real benefit, as in real increases in their profit margins. So what this shows you is that there is a benefit and there is light at the end of the tunnel, but people do need some help getting the their experimental machine learning advances into the production flow. And particularly from the point of view of a data scientist, who's usually the one who created the innovation, it's very important to be able to get the innovation out into production so that the company that you're working for can actually see the benefit reflected in their bottom line and their revenue. So that's what we're going to talk about today. So why is it that it's challenging to bring machine learning into production? So part of this is that, like many other development projects, machine learning has an experimental stage where, which we are calling the data science sandbox. This is the stage where people are experimenting with algorithms, they're testing them out with data sets, they're trying to figure out what algorithms might work, which ones don't work. And then success for the experimental stage is that you found one or more promising algorithms. Then what happens is that in order for these algorithms to actually be used by the business, then they typically have to be put into production, and that usually involves another group of people or at least a different set of skill sets. And so this is what we are talking about regarding the sort of the transition from sandbox to operations. There's a number of things that make this challenging. One of them is the diverse focus and expertise between the data scientists and the operations team. So data scientists typically tend to be experts in algorithms, some mathematics, the nature of the data, things like that. And operations teams are usually, experienced with uptime, handling, distributed system software, worrying about security challenges and things like that. So and these two teams have to work together successfully to make the, machine learning advances work for the business. There's also, unique things about machine learning, like, for example, the fact that the results are so data dependent, they're so dependent on the hyperparameters used in the algorithms, things like that, that make it even further challenging because the machine learning applications have unique needs that really only the data scientists really fully understand. So these are the things, some of the things that need to be addressed so that you can bring these algorithms successfully into production and keep them healthy in production. So what we are, focused on as a company is what we call MLOps, which is shorthand for machine learning operations, and reflects the full life cycle of machine learning, management in production. The first thing that's important to realize is that this is much more than inference. So inference or model serving is an important part of production because that's how you actually use the model to do something. But there's much more than just being able to set up an experimental serving endpoint to create a fully successful production ML. There's other things like, for example, you have to make sure that the ML applications remain healthy during production. So particularly if the incoming data drifts, if there's bugs, if there's unexpected patterns of prediction, you have to be able to diagnose those and detect them. If you are in an industry that has any kind of regulations, and what we are seeing now is that different industries are seeing different types of regulations coming out from machine learning. Some are subject to the General Data Protection Regulation coming out of the EU. Others have specific things because they're in healthcare or in, are in autonomous cars or in financial services. And so it's important that the machine learning be able to work with the regulations that the business has to operate on. Then the third thing is that fundamentally the machine learning algorithms have to result in a positive impact to the business. And so what most managers are concerned with is whether or not the overall application did better as a result of using the ML. And so you need to be able to showcase that and help the algorithm to assess how well the algorithm is doing relative to the business needs. And then there are many related things, like, for example, there are security implications of using data. Sometimes different businesses, they need to understand which human did what work in order to make sure that if there's a lawsuit or something like that, they know that they've been able to protect themselves. So these are several of the things that really have to be done in addition to doing good model serving that are there to make the business successful. So M-Center handles each of these things, and we basically do it by executing what we call the AI control plane. So we manage machine learning on different kinds of compute platforms and engines so that data scientists can bring in any code that they like. They can create custom code, they can leverage code that is used in the open community, they can tweak it and all of those things. And then we allow you to run those on different analytic engines of your choice. And then we manage all these other areas that become important for successful production. So in short, this is kind of what the MLOps does and what MLOps is about. Incoming is promising models that you've experimented with in your data science environment. You can use a variety of different tools. We'll show you something through a Jupyter notebook in the demo. And then we basically manage all these aspects of it, which is everything from actually automating the code, automating the pipelines, to making sure that you can do machine learning specific diagnostics. Well, you can assess how well the applications are, benefiting from the machine learning algorithms that are being used in production, as well as tracking everything about what model was used, when and where, so that models can be rolled back if necessary, or if you wanted to create an audit trail, for example, then you can understand exactly what was used and when and why. So this particular pie chart reflects all the different things that we really consider to be part of a machine learning production. And what you really want to do is to be able to make it really easy for a data scientist to be able to bring their work into production by using a tool chain that will simply take care of all of these things, so that they don't have to worry about these things themselves. All they have to do is to bring in their code, and then this stuff just works. So the approach that we're taking is a completely software-oriented approach. So for those of you who are, kind of more code inclined, these are basically a set of Docker containers, and you can install them in any environment of your choice. So you can dump them into a private data center. You can put them on Azure, on AWS, on Google Cloud Platform, wherever you'd like to run them. And they manage essentially a number of what we call analytic engines. So an example of an analytic engine is some kind of a runtime where the pipelines that you guys write will be running. And so examples of analytic engines are things like Spark and TensorFlow. I think we'll be using Spark in the demo today. You can also write your own standalone Python programs and create containers out of them and launch them as containers. So that gives a data scientist a great deal of flexibility of the kind of code that can be given to their operations teams or to their production teams. So you can take, practically any code that will run in any of these environments, and that can be the code that is handed over to the production. And then that code will be managed through our environment. And so you see on the left side of this diagram a number of different data science platforms that data scientists can use to do the initial experimentation that then can be brought in seamlessly into the product. So to help understand kind of how the product works, we'll go through a little bit of a depth of kind of what we do inside the product that enables a lot of data scientist sophistication to be done, and then we'll showcase some of these in the demo. So one of the fundamental things that we do is we allow a data scientist to model what we call a machine learning application, and internally we model this into a graph that we call an ION, or an intelligent overlay network. The basic idea here is that you can specify all the pipelines that you think are important to run as part of the machine learning application. So an example might be that a very, very simple example is if you created a model that you've trained, say in a Jupyter notebook somewhere, and all you want to do in production is to do inference or model serving of this model. Then this is a graph of exactly one node, and that node is your serving pipeline. If you decide that you want to, retrain once a month, and you want to create a training pipeline that you'd like to run, once a month, then now you might have a graph of two nodes where you have a training node that runs once a month, and you have an inference node that maybe runs every 5 minutes, something like that. If you have a much more complicated one, you can still describe it as multiple pipelines. So if you have an ensemble training, for example, or you want to compare models, or you want to vote on multiple models in production, all of that can be specified as a machine learning application. This is important from a data scientist perspective because the operations people are really not well versed in why you want the multiple pipelines and how those pipelines should be related. So this gives the data scientist a way to really easily describe and very deterministically describe a set of related pipelines that then can run in production the way that the data scientist would like them to run. And there's enough information for the entire process to be automated so that that makes it easy for the operations team as well. So what we're now a little bit of technical detail, it's basically a graph, and each graph node is a pipeline. And that pipeline is a DAG the same way you might see any other kind of DAG like a pipeline. So you could have a source for data, you can do some processing on it, and then you can create a result. And then what we do is we take this pattern and we execute this pattern, and we put this pattern on distributed analytic engines so that it can run wherever you'd like for it to run. So a simple example, a very simple example, is you can see one here that has actually 3 nodes in it. What this basically says, and I'm going to go through this in a counterclockwise manner, starting with node 1. Node 1 is an inference pipeline or a model serving pipeline, and it runs every 5 minutes, and it's the one that actually answers any prediction question. This thing is fed once a week by a retraining pipeline, where if I have new data, I can retrain the model. If I have and that retraining pipeline doesn't happen every 5 minutes, of course, it happens once a week in this case, and it runs on a different Spark cluster. When there's a new model, I may want to have a human approve it, in which case I would have a policy node that says, okay, a human is going to approve this model, and if the model is approved, it will be pushed to inference. So this is a very simple example of the kind of graph that you can draw that will then completely specify how the production operation is expected to run. So then what do you do? So what do you practically do to get this stuff working in production? First thing you do is you define this graph and you write this graph as a JSON file. And here's a simple example of a capture of a JSON file. And we'll go through this in a bit more detail in the demo. Then you bring in your own code or any code that you're using. So it doesn't have to be code that you wrote. It could be code that you took off like Spark ML or a TensorFlow library and then maybe tweaked a little bit or just left alone. You bring that code in, and we'll show you kind of how you might instrument that code to get what you want out of the production environment. And then basically you give this JSON file and this code into the environment. And that is basically the only thing that is required to get the full production flow running. And then after that, the mechanisms in the in the M center will read these things and essentially deploy and execute them and create an environment where you can collaborate and work with your ops teams to study how it behaves. So an example of how you can even do this for much more complex applications. So here's a quick ion that we drew for a much more complicated production pipeline. So here what you have is you have an ensemble model, and you can see that it actually has 3 algorithms within it, or 3 models, and each one of them could be periodically retrained. Then you have those models, and they're going to vote amongst themselves in the inference pipeline. And you may also have a control pipeline, which is a much simpler model that you run in parallel just to make sure that your very complex model is behaving in a stable manner. So a simple example of something like this could be you may have a very complicated ensemble running in production, but you may have, like, for example, a really simple logistic regression running alongside it, just to make sure that, the majority of the time, the 2 things are behaving kind of the same way. And that helps you in 2 ways. It helps you track and make sure that everything is relatively stable in your more complicated model, but it also gives you a very quick way to roll back to something much simpler if something goes bad in production. for example. And so you can create everything from a very simple type, graph to a very complicated graph, and still be able to know that people without machine learning knowledge can actually deploy these in production and deploy them exactly the way that the data scientist intended. So finally, a comment about model serving. So model serving is, there's many terms out there for this. Some people call this, serving, model serving. Some people call it inference. Some people call it scoring. It's fundamentally the action of executing the inference. We support a number of different inference models or serving models. So you can bring in REST endpoints. So if you have a web service or something that needs to consume these predictions, if you have a streaming service that needs to consume them, or you want to run them as batch, we support all of those combinations, and you can run them on all the standard, environments like Docker or Kubernetes. You can orchestrate them through Kubernetes, provision them through Yarn, run them through a cloud vendor, and things like that. And everything that is served here is completely complemented with the machine learning production features like governance, monitoring, business KPI, things like that. So in order to do serving, fundamentally, you can either upload a trained model and some inference logic, or you can allow the model to be retrained in production. You launch it and you can package it up, for example, as a container, or send it into a standard runtime like Spark. And then we will deploy all of those for you. And then your business application will essentially send requests to these to the deployed inference runtime, and those requests could be sent in via Stream Broker, they could be sent in via REST endpoint, or you can just put all your requests in a file and run a batch job against it. All of those things will work in this environment, and depending on your use case, you can pick whichever one you like. So if you have, like, for example, a light web service where you need real-time predictions, but the volume is relatively low, then REST serving works really well. If you have something where you have a device, like an IoT device, and you have, a tremendous volume of predictions that need to happen, and they all need to be at low latency, it's typically better to use something like a streaming application. If you're doing something like a customer recommendation where you don't really need it to be real time, but maybe every day you'd like to reevaluate the customer's preferences so that you're ready for them the next day, that's more of a batch serving kind of use case. So for machine learning, for a data scientist, really the MLOps comes down to three fundamental things. So step one is you bring in your code. And as we've said already, you can bring in code or algorithms or even feature engineering and other kinds of things for various types of engines. You can also upload pre-trained models if you'd like, and you can do that in any format. So if you'd prefer to do the training offline and not in production, then you can just bring in the model. That works too. There's a rich array of built-in components, which Craig will show you during the demo. So you can also use built-in components. You don't have to necessarily write your own. You can also keep your code in, Git, Bitbucket, or we can version the code for you, depending on what what's normal in your environment. We provide a number of different custom features for machine learning, which you'll see in the demo, and and they include A/B and canary comparators, meta-learning functions, analytics, health indicators, things like that. Then once you have your code running in production, then effectively the product allows the data scientists to seamlessly monitor everything that's going on in production if they would like. So, and the reason this is because everything that happens in production is fully monitored, and different people in the company can have accounts where they can log into the runtime, and they can see what's going on in production. They can also take captures of what's going on in production and bring them back into their environment. So the product creates a collaborative place where data scientists can collaborate with non-data scientists, so people like operations, IT administrators, to take, see what's going on and get visibility, and when needed, to control it as well. Finally, you can bring the studies from the production environment back into your data science sandbox. So you can download statistics and lots of details from the production environment. You can bring them back into, for example, your Jupyter notebook, you can crunch them, and you can use those to make your next round of algorithms better. So that's really sort of the production life cycle as seen from the point of view of a data scientist. So what we'll do now is we will switch into the demo, and Craig will actually take you through one of these potential life cycles. Craig, you would like to start sharing?
Sure. You stop sharing your screen?
I did.
Excellent, thank you. So, hello everyone. I'm going to take you through a little demonstration of what Nisha just described. And to do that, I'm going to use the example of a day in the life, right? So going from a data scientist's raw code, how to prepare that code to be used in MCenter, and then actually deploying that into production and monitoring its health. So to that end, you can see that I have a sample of code here in a Jupyter notebook. And what we're doing is a simple logistic regression on a public data set. This data set is tracking human activity using smartphone sensors. And what we see here isn't too unexpected, right? So you import your usual machine learning libraries. You bring in your training data. You then split out your features. And then we're performing a hyperparameter search and using a k-fold cross-validation. So far fairly typical. Then we use our search to find the parameter with the best average accuracy, so we can use that to make our prediction. We have some optional code where we print our label distributions. But the really important part here is that we output a pickle file, right? So that it can be picked up by our inference pipeline, which is further down in the code. So we bring in our our model. We bring out we bring in our test data. We extract our features, and we make our prediction. And going further, we have some extra code where we're actually showing our confidence in our predictions. So our low confidence and our high confidence. Now this is optional here, but this will actually come in handy when we're monitoring health in MCenter. So let's proceed further. And so the question becomes, how do we take this raw code and make it usable by MCenter? And we do that by with two sort of features. The first is the JSON file, and the second is to actually use our machine learning operations API. So what I've done is actually I've split the code into two portions, the training portion and the inference portion. And for the most part, the code looks the same, right? I've added a few lines though. So I'm sorry, let me, so up at the top, I have added my API calls. So I actually brought in the library. So I've brought in 4 things here: the stat category, bar graph, table, and the actual API itself. And then as you proceed through our code, there's not many changes, right? Nothing so far. Until we get to here. So we first initialize our API within the context of the compute engine. And as Nisha mentioned, we're using the Spark engine. So we initialize it in the Spark context. And going through the code, it's what we had before. There's nothing new here. Until we get to our hyperparameter search. And what we're doing here actually is we are going to track the statistics. So the values that are being generated by the search, so the parameter, the regularization parameter, as well as its accuracy. We want to track that through iterations of our component being run. So every time we do training, we want to track how that's going over time. And so, this first line of code here, this is from our table API, and it brings in, we create a table, we name it, we track its column, and then for each regularization value in the search, we add a row to that table. And then we make our final call a set stat. And what this does is it tells MCenter that you are going to be tracking this particular statistic, this table, that you're going to update it, and that it should be made visible via our health UI, so that you can actually see what's happening as a table. Then we proceed further. And you see no changes, so label distribution, this is what we had in our code beforehand. But what we're adding is a bar graph. This bar graph is actually showing a label distribution, that we built initially. So it works in the same method. We bring in bar graph from our API, and then we do a stat. And set do a similar thing in that they tell MCenter to track this statistic over time and to make it visible. Right? And then finally, we do the same thing for our cross-validation accuracy. So we want to track that over time. And again, what I want to reiterate is that these stats are collected per run of the component. So per run of this training pipeline is when we will collect these stats. And then we've left our save model code here. So now that we have our code instrumented, right, we can now actually, MCenter can now actually take your code and monitor it for you in production. Our next step is to actually tell MCenter how to interpret your code, how to actually understand it, what everything means. We do that by means of a JSON file we call component.json. And what it does is it specifies all the necessary metadata on MCenter how to deploy and run this component. So as I said, we're using Spark, in this case actually specifically PySpark as our engine to run this code. We tell MCenter that it's a Python language. We tell MCenter the name, the label, and also the file name so that MCenter can find this code in the first place. And then we have this piece of this line here defining model behavior. So what we're doing here is specifying what the component does. So generally speaking, ML pipelines, they either produce something or they consume something, a model, right? So since this is a training model, so we label it as a model producer. And then further forward, we group the component. So in MCenter, we recognize several types of components, algorithms, so machine learning algorithms. We recognize feature engineering. So if you need to actually, vectorize data, for example, we recognize sinks and sources. So these are all things that we recognize. So we require that you group your code into one of them, so that it's easy to organize, easy to see, easy to find. And then the next thing we define is whether or not this component is using the MLOps API. And as we just saw, we are. So we notify MCenter that yes, we are using it. So MCenter will then make sure that the API is available to be called. And then the next two important components of this JSON are the actual arguments. So, a component generally takes things in, arguments, things that it has to work with. And in the case of a training pipeline, what you want to make sure that is that you have a training file, training data. So that's what we specify here, is that it's required, you need to specify a file to contain training. We have a second optional argument. So if you want to, say, output the model, to some directory on your system, you could do that, via this second argument here. Now, this is optional because internally within MCenter, we track everything. So whenever a model is created, whenever a model is consumed, we track that creation in that location so that's available to be used by other pipelines. Okay. And we do the same thing for our inference. So with the inference code, we include, for example, a bar graph. So that high confidence, low confidence in the original code, we're actually using it here, creating it as a bar graph, that it can actually be viewed in the Health Center UI. We do the same thing with component, but the major difference here is that the model behavior is now a consumer. So this is an inference pipeline, so it brings in a model that's already existing. And then our arguments, again, are for an input file, so you need data to test against. So we require you bring that in this particular component. And then we have the option of specifying a particular model if you needed to. So if your model is in some other directory that wasn't being tracked by MCenter, you could specify it here. Okay. So with that, we've componentized our code. We've taken our raw code. It's now ready to actually be used in MCenter. So the question is now, how do you get it into MCenter? Nisha mentioned that we can use Git. So I'm going to actually show you that right now. So as a caveat up front, I'm going to be doing all this work as a single user that's been provisioned and permissioned to do all these things. But generally in an actual production environment, you would split things between, an admin user that would provision resources and the data scientist users that can build their models and build their, their application. So step one, bringing the code in. So typically the admin would connect the mCenter instance to your Git repository. That's usually the best way to bring in code, right? So that so that you can track changes, that you can commit changes, and ensure that you always have the latest version of the code available for use. And so you'll see here that I've already connected to a repository in Git, and the repository itself is right here in Bitbucket, and the components that we just built are already uploaded. So lr_train, lr_infer, as are their component.json files and their actual, Python code file. So now that we have that code, it's ready to be brought in. How do we bring it in? And if we come to the onboarding section, I'll go through all of these things, going forward. But what we're going to do is actually come to components and bring in our, our lr_train and lr_infer components. Now, for the sake of this demo, I've already uploaded them, so they're already available to be used. But what we can do, I'll briefly show you how we would, bring these in. And we do that via the register remote component. Yeah. So anyway, sorry for the glitches, people. But so we bring in the component, we register it, it's in here. Now we can actually use this component in any pipeline that we want. So you see here that I have several built that already, but I can actually show you very quickly how to actually build a pipeline. So come over here to create pipeline. You give it a name. I'm going to call this, train logistic, test 2. This is in PySpark engine. Create it. Now what you'll get is a, fairly standard, graphical canvas. We designed it to be familiar. We didn't want to rewrite the book here. We wanted you to focus on actually building your application and deploying them.
Sorry to interrupt, Craig. I think somebody is typing on the. If any of the panelists are typing, can you please stop typing because it's distracting the people on the call? I thought it was me, but it wasn't me. So please, whoever's typing, please stop. Thank you. Go ahead, Craig.
Sorry for that interruption. So what you do is you click that you add algorithm, right? So you're going to add something to this pipeline. So you click that algorithm button over at the right. It'll add a node for you. And now we're going to click on this to add the algorithm to it. And on the right, you'll see a menu come up. And from it, you can select, any of the components that are available to be used as an algorithm. And you'll see that we have our train logistic and our infer logistic. So we'll use the train logistic regression algorithm that we just uploaded. So now we'll give it the data file that's required. And now, the key thing to note here is that the component.json is directly interpreted by mCenter. So it actually constructs this for you. So I have a file on the system in temp. So I'll load it here. And then, so the output file location is again optional. We don't need to fill that in. We'll save. And now you'll see that it's available here to be used in any sort of application. So creating an ion, the application is pretty much identical to building out the pipeline itself. It uses the same sort of graphical interface. Okay. So again, the create window comes up. Create it. And we have our GUI here. So, we initially just, set up a single node You need at least one to have an application. And this will contain the actual pipeline, the actual components and code that we've written. And what we'll do first is actually set this up. So an ION, like as Nisha pointed out, encapsulates the code, the components, the pipeline, the logic defining the application, as well as the engines that run your pipeline. And to bring together all these things, so this empty node, the first thing we set up is a group. Now, a group is a way of organizing your engine. So it could be that you have multiple engines, Spark engines, Spark clusters for training. You have other ones for, doing your production, your inference. You might have TensorFlow engines. You might have Flink engines. You can group those together to make them easier to manage and deploy them. So we have a Spark engine, and it's part of the Spark group. So we'll select that here. So it's set. Now what we'll do is actually assign a pipeline to this node. So to actually do work, right? So you'll see from our list of pipelines that we have, everything that, is on that pipeline list is available here. So I'll use the train log regression component that I uploaded earlier. And so now it's actually part of this node. Now, our next step is to schedule. So each individual node can be scheduled. So you can run your training on different schedule from your inference. And you can train, we have the simplest schedule, so you can train things to run every minute, every hour, every day, every week, every month, things to run every day. Or if you so chose, you could provide cron type scheduling. So we have a manual input scheduler. So if you prefer to use cron, you can do that here as well. We'll leave it more or less at the default, for 5 minutes. And now what we're trying to do is save it. Now this warning comes up because an ION, an application, is more than just its base units. It's more than just its engines, its pipeline. What it is also its policies, the rules that govern its behavior. So when you go to save an ION, your application, we ensure that you define policies, that you've defined those rules that govern how this thing is supposed to behave. So we'll come to the Add Policies window. That's up here at the top right. And what you'll see here is that we have 2 policies out of the box. The first is model propagation, and the other is model health. The propagation policy defines how the model should be pushed forward. Should it always be pushed forward automatically? So whenever the training produces a model, should it automatically be pushed to the inference pipeline, or should it be manually approved? So that whenever something is generated, we send a message saying, oh, there's a model, you need to review it before it's approved to be used. So for the sake of this demo, we'll say always propagate. And then once we've done that, we need to actually specify health. So data deviation is something that we monitor out of the box. And what it is that when the inference is running, generating its inferences, mCentral will compare that against the inferences that were made during training to see if there's any sort of deviation between the two. And what this can indicate is perhaps the model's having, might be the model isn't quite right, or perhaps the data itself, the distribution has changed, since you trained. And it's something that you need to look into. So what mCentral will do is it will alert if this threshold is, crossed, so say that the deviation was at 0.79. That would mean that's below 0.8, so an alert is generated. We'll leave it as at default for now. Update our policy, and then it automatically saves for us. We'll add our second node so that we can do our inference. We'll ensure that it runs after training. And then we can save, because we already have a policy defined. But now we need to make sure that node 1 is talking to node 2, so that the model gets transferred. And we do that by dragging and dropping a connector. So now this application is ready to be run. It's actually fully built. We have training happening, we have inference happening, and it can be deployed. So something to notice though is that our options to launch are limited. So we can launch in sandbox or in production. Now, to launch in production, generally you need to be permissioned to do so, right? Production is tightly controlled, it's tightly accounted for. But sandbox, that's our testing area, right? Our experimentation area. So data scientists can generally launch there by default. So we will launch this in sandbox. And we have options to use a predefined schedule or to run now. So predefined schedule, we just define our schedule. So what would happen is that the training would run in 5 minutes from now, and then the inference will run 7 minutes from now. Or if you want to do the experimentation immediately, you can force a run now for X number of iterations. So we'll choose run now, and we'll choose, say, 10 iterations, and then we'll launch in our sandbox. And so we send a message, it's been launched. Now where we'll observe it is in the dashboard. So this is where we can see at a glance what's happening in the system, both production and in sandbox. And if there are any alerts being generated, right? So there's health issues. And so what I've done prior to this is I've already launched other ions so that we can have things to observe. You'll see that we have ours launched, log reg test 3, and it's currently running. But we have another one launched in production. It has a health issue. So what I like to do is to actually show you, how we would diagnose that. But first, I'd like to show you how we can observe and, see all these things, the data that we display to help you monitor health. So moving forward. So the data scientist view. So the data scientist view, what it does is it gives you a high-level view of everything that's happening in the components in the system for all of the runs that have been happening. And so, you can view each individual component. So you can view the training and the inference, each component separately. But within node 1, what I want to point out is these 3 graphs. So we have a table, 2 graphs. So these are exactly what we built into our code using the MLOps API. So as you're building things, as you're monitoring things, MCenter is interpreting your component and building out and tracking your stats. So we're tracking these 3, and MCenter makes them available, makes them visible, and we'll track them automatically for you over every iteration of this training run. Okay. So you can see the hyperparameter search results and the accuracies. You can see how label distribution is happening, and you can see how the accuracy of the cross-validation is moving over time. And that's all you have to do. You didn't have to actually code these things out. You just have to make them available to MCenter to be tracked, and it did it all for you. So you can track any number of statistics, not just 3. You can track, and it doesn't have to be those ones that we've done here. It can be any statistic that you think is relevant and valid for your algorithms. Okay. In here, we're looking at the regression. And again, these graphs that are being generated are coming directly from the statistics you're tracking in your code, that set stat that you've done. So, tracking the number of times the model has been accessed by the inference pipeline. You're tracking the low confidence distribution and the high confidence distribution. And that's all out of the box. All you have to do is tell us to track it, and then we do. And then, so you can see here the model plot. So initially, of course, when it first ran, there wasn't a model, so it said as much. But then, when the training finished, a model was available, and you can see that happening here as such. So as we go forward, we can see, we can get our values. And something else that you can see within the data science view is the actual events. So you can see every event that has happened since this particular application has been launched. So you can see when the inference pipeline is activated, when training pipelines came online, and you can see when alerts are generated. And you can also change your time window. So you can view everything that happened within the last 10 minutes or within the last 6 hours. Or you can specify a custom time, right next to it. So we'll look at an hour. You see how things change. Excuse me. And then something else we collect are logs, so the system logs themselves, to actually make them available, for operations people, because we know that this can be hard to find sometimes. So as I mentioned earlier, that this particular application has a health issue. So we can click on it, here, to actually see what that is. So we click. And what we see is that we're having a data deviation event. There's some difference between what we saw in training and what we're seeing in the inference. So, what you see here is, for example, a heat map to actually see if the data is changing over time. You can see the input data distribution between training and inference, so you can see how things are differing. So you see that there is a difference for this particular input, this particular feature, and the similarity score is 0.57289, which is lower than our threshold. So it's something that we have to alert on. We're notifying you that there is a significant deviation. You might want to look into that. So you scroll down, you see more. Now this isn't every feature necessarily. It's just the top features, just because it could become a very long list. But you can see the full list here in the alert window. And so this message generally will be first seen by the operations person, the person that's actually monitoring the system. So they'll see this, and it may be that they don't have the knowledge of your model to make a diagnosis. What they can do is they can help the data scientists make the diagnosis. And you see here, they do that via what we call a capture timeline. And what this is a snapshot of all the events that happened in this application within a given time window. So, you give it a name, whatever that might be. And then you give it a time span. So we can do up to 2 hours. So we'll go with 2 hours. And then we click capture. Now the capture is effectively instantaneous because we monitor all these things in real time. So when we take a snapshot, all the data that we need is right there immediately available. So we created it. And now what we can do is actually pass it along to the data scientists. We'll notify them saying that there was a health issue with this application, and here's the snapshot of what was going on. And so now what the data scientists can do is they can log in, and they can come to the timeline capture window. And what it will give them is an actual view that we just saw. But now, unlike previously, it can be sliced and diced within the given window via this timeline bar. And so the data scientists can try to narrow in when this alert happened, with the exact moment that things occurred. And they can see, all the details, they can see everything that happened. They can get a very good view of what's happened in the system that might have generated this. Or it might be the case that, this doesn't give them quite the details that they wanted. They might need more. So what they can do is they can actually download this capture. And what it will do is it will, tar up, it'll zip up, compress all the metadata that we collected for this particular run of this application. And it's a set of CSV files. And so what you'll have is, all the data that is available in the system. And once it's downloaded, it's now available to be analyzed via any tool you prefer. You can use any language, any tool. We're agnostic to that. It's just, CSV file. So what I've done is I've built out another notebook in Jupyter to do this analysis. And what we're doing here is we bring in the snapshot, we untar it, and this is a sort of a simple analysis. And what it does is it lets us look at the individual features to see how those features are behaving over time. So this is a list of all the features we have. And I've selected this, T-body act jerk max Z. So this is the feature that measures rapid movements of the body in the Z direction. So, we run it. And what it does is it generates a little histogram. So it lets us see exactly what, happened with this particular feature. And we can do this for any feature. And of course, the analysis could be in any way or shape or form that you want to analyze things. This is just an example. So from our analysis, what we've concluded is that it's not the model that's at issue. The model is behaving as we expect, and the data is falling within the distributions that we expected. The error isn't being exceeded. So what we've concluded is that it's not the model, it's not the data. What it is actually is that our threshold, our monitor, is just a bit too sensitive for this data set. So the data is coming off of smartphone sensors. So those sensors aren't the most accurate, and they can be really noisy. So that's really what we're seeing. It's just that noise in the system. So what we can do is come back to mCenter, and depending on permissions, so it might be that the data scientist can change these system details, or they might need to notify the administrator to do it, but we can actually manage the health. We can change those thresholds. So in the actions menu and on the UI, you'll find health management, and you'll see data deviation. So we can do a global level or at the individual feature level, and we can adjust it. We can change that threshold. So global will affect every feature equally, or we can go further, and if we're sure it's only one feature or maybe a handful of features, we can actually just override those specific ones. For the sake of this demo, we'll do it at the global level. We'll change it to 0.5 because we saw some of the similarities were really low, like 0.55, 0.57. We'll update health, and then what will happen is that on the next run, the next iteration of this application, the new health metric will be captured and applied. You'll see that now our health is back to green. So we've resolved the issue. And so, what we've seen here is actually how to take your code, your raw code, and bring it into production, very easily, very simply, very quickly, with very little overhead. So, that concludes what I want to show you. So I'd like to open the floor to questions. Thank you.
So I think the bulk of the questions were actually answered during the. I think there's one additional question which I'll just answer live. The question is, how does this solution handle model retraining and feedback? So the model retraining is something that you can schedule, as part of the pattern descriptions. You can create training pipelines, for example. You can also do training in sandbox and then push those models into production. So there's a very rich array of ways that you can do model retraining. The feedback is gathered in a variety of ways. As we've shown during the demo, the model, the tool maintains full kind of history of all of the statistics, so you can understand the historical behavior of your predictions, how they correlate with the models that you pushed into the system. You can do customized post analytics on it. So there's a host of ways that you can get feedback in terms of how the model has been behaving in production. And as Craig showed, you can also take that feedback and take it out of the system and crunch on it in your development environment as well, if you'd like. So if you wanted to, for example, look at some of the models that were used in production and see how they did, you can also analyze them on your laptop and get more insights and keep those yourself. Everything that is kept in the runtime, in the production runtime environment, is versioned. It is kept in a database. We basically allow the customer to either specify the database of their choice, or we bundle a MySQL database. The reason this is important is because this means that your production teams can essentially keep all the statistics for as long as they would like, and they can give you access to it to mine to your heart's content as you wish, because it's basically a database. And so that's a very normal thing for people in production to handle. So it'll be very easy for them to keep any statistic they want. And because the product allows you to have multiple accounts, you can basically go and mine those statistics if they've given you permission. There's one more question here. Yeah, unfortunately, the governance tab was actually not part of this demo. But effectively, the governance tab allows you to try to, I don't know, Craig, if you have a view of a governance that you could share with him on a screen or something like that.
Sure.
That might be the easiest way.
Where is this? Yep, here we go.
Okay. You want to start sharing something?
Yeah.
Okay. So Craig is going to share with you guys the governance tab. Thank you for the question.
Where is?
Okay. Yeah.
Can you?
Yes, we can see it now. Go ahead. Mm-hmm.
So this is our governance tab, and what it lets you see is the who did what, when, and why. Okay. So who did what, when, and why in terms of models. So for any given model that's been generated or uploaded into the system, you can actually, when it's created, you can see, who was created by. You see which ions, which applications made that model. You can see, very specific instances. So each instance of an application, you can view that way. You can look for, PML models, save models, binary, text, and from all sources. If you could have multiple engines, right? So we only have one engine here, but if you had multiple ones, you can see them all here. And then if you dig into these models, so for example, you can look at this particular model here. So this one hasn't been used, but it was generated. I'll look for one that was, see here, generated from ion. So which one is it? There it is. So model generated by this, this is actually the ion I just showed you during the demo. So we'll look at one of the older models, and we can see that it was generated, that it was approved for use by the MLOps user, what ion generated, what instance of it came from. You can see the pipeline that made it. You can see when it was created, and then its approval or rejection status. So who approved it, and then actual usage. So you can see when it was used and what used it. So you can see that it was used by the log regression application, by the infer log regression pipeline, and for how long it was used. And all these are clickable. So if I clicked on this ion here, it would take me right to that ion. Or I can click on the pipeline, and it takes me right to the pipeline. And so that's how we manage governance. So you can always see who did what, when, and why.
Great. Thank you, Craig. So a couple of other questions. So one question is your platform agnostic as to regards language? So basically, this platform provides a number of languages. The way we look at language typically is that you can run any program that will work in any of the runtimes that we support. So for example, if you want to write a Spark program or a TensorFlow program or a program that runs inside a container, those are the kinds of environments that we support. We are adding support currently for R in these types of environments. The primary languages we support today are Python, Java, and Scala, and we're adding support for R. In terms of SaaS, we're adding support for SaaS on demand. Basically, there's been a number of requests for SaaS, but right now SaaS is not one of the engines that we support. Depends on on exactly what you want to do with that. So that's the answer to that question. Then I think there's a couple of other questions. Is this exclusive to online deployment? Is there an option for offline or limited network devices? So basically, I think let me try to kind of break this down a little bit. First of all, there's definitely support for limited network devices. So particularly the model that we have, where we have servers and agents. If you can deploy a pipeline in a remote environment, and that environment loses network connectivity, the pipeline will continue to run. The only thing is that it will not be able to send you any statistics until it can reconnect again. So there's a provisioning for saving the local statistics and keeping them locally buffered if the engine is unable to connect. So if your container or your engine that's running the pipeline can't connect, it will keep its stats around by itself, and it will give the stats to the server when it connects next. So you can do things like that. If you're fully offline, then in that case, the server environment would have to be with the pipeline, because otherwise you will not be able to communicate. It depends on what you mean by offline, really. You don't have to be cloud connected if that's the question. You can be completely on-prem and completely disconnected from any cloud, and everything will work. I think I hopefully covered all of the questions. If there's no other questions, I think we're right on time. So thank you so much. I appreciate your time. And if you have any other additional questions, please feel free to reach out over email. And the slides will be made available. There was also another question about whether the link to the Jupyter Notebook could be included with the slides. And I think we can accommodate that.
Sure. Yeah, we can do that.
Thank you so much. Appreciate it.
Bye, everybody.